Hello everyone! Welcome to today's video where we break down the design of Singulariti version 2. As you may have seen before on its videos, the original Singulariti was the 3-pound egg beater style vertical spinner that the Georgia Tech RoboJackets team that I was part of built together. Singulariti version 2 is a completely ground up design that I worked on mostly by myself in the past few months. It is also why I have decided against using the naming scheme that involves adding an extra I onto the name, since that is a RoboJackets tradition. Singulariti version 2 features brand new components. Here's some that has already been made. Some laser cut titanium parts. This is the front anti-horizontal wedge. Some laser cut carbon fiber. These are the top panel. We have some steel wedgelets. These are for fighting control bots and other vertical spinners. And of course, this brushless weapon motor that I have coated internally with epoxy. However, while being relatively ground up, Singulariti version 2 shares the same configuration. It incorporates all the lessons we learned when making Singulariti version 1, and a lot of the thought processes that proved to be very effective were also applied. Our RoboJackets 3-pound team was absolutely amazing, and I hope this design lives up as a worthy successor. Before we look at the CAD drawings themselves, let's first break down the design goals that were set out. First of all, when we were working on Singulariti version 1, I think we got a lot of things correct in the design concept, so there is going to be a lot of carryover. All the good things that prove to be effective in combat. We are of course keeping the overall configuration and layout. This is more of the specifics. The first thing that we're definitely keeping are brushless motors for the drive system. The brushless drive on Singulariti version 1 was able to save us a lot of weight compared to the other bots in our 3-pound program that were running brushed motors with planetary gearboxes. It was also shorter, so it made packaging easier, and it propelled the bot at higher speeds than any of our opponents, which made us able to determine when and where in the arena to engage. The second aspect that we're keeping is the ability to quickly swap in different setups. Being able to switch from the closed center wedge to low forks and an open center wedge was crucial to our wins against control bots and vertical spinners, and definitely something that I wanted to keep for the new design. The third element that worked really well was the heavy use of puzzle fits in the chassis. Before Singulariti, I did not really utilize puzzle fits for bolted components except for wheel guards, but everyone at the Georgia Tech Club really advocated for them being heavily used, and it ended up being a very good idea. Not only did it help the chassis stay together and took the stress off the screws in many directions, it also made aligning the panels every time for assembly much easier, which saved a lot of time. Now we get to the really interesting stuff. The goals and ideas that separate this new version from the original, and hopefully make this new version perform even better. First, I intended Singulariti version 2 to run a live shaft configuration for the spinner. This was so we could put the bearings in the chassis and then integrate the shaft into the two ends of the egg beater itself, saving all the weight of the dead shaft in the middle and allowing us to put all that weight into the weapon. I also wanted a larger weapon motor in the 40mm range. The small 2826 motor had extreme overheating issues and made spin-up time relatively long, which hindered the use of our fast drive. Having a bigger weapon motor should allow us to spin up much faster and thus be able to engage the opponents sooner. Singulariti version 2 was also intended to run timing belts for the weapon instead of round belts as a result of the more powerful weapon motor. A 4-cell lithium polymer battery was also a design requirement for version 2, one more cell than the 3-cell battery used in the original. Higher cell count in series gets us higher voltage and thus faster motors all around. For the chassis, instead of aluminum, the idea was to use mostly lightweight plastics and composites. This allows us to design a wider and longer bot for the same weight, increasing wedge width and stability. The closed center anti-horizontal wedge was also required to be made out of titanium alloy instead of steel like the original. The higher specific strength of titanium will allow us to get the fork setup and the closed wedge setup to be much closer in weight than version 1, where the anti-horizontal was the full weight, but the fork setup was much lighter. I also set out to design more space for electronics inside the chassis. The first Singularity suffered 2 failures caused by the cramming of the electronics, one breaking through solder and one wearing out the weapon motor wire. Giving it more space will allow for less stressed packaging of electronics and thus, hopefully, more electronics reliability. Lastly, it was decided to use gearboxes to transmit power from the motors to the rear wheels, then belt driving the front wheels instead of belt driving both front and rear from the motor. The 3D printed timing pulley that was mounted onto the motor in the first version of Singularity would last only about 3 to 4 minutes of driving before it would either be snapped in half or stripped from the torque and repeated wear. This was likely made much worse because that pulley had to be very small because of gear reduction requirements. Having a gearbox drive the rear wheels would reduce the number of belts and eliminate the need for reductions, and thus increasing the reliability of the drive system. The design process itself took approximately 3 weeks to get everything sorted out. And here's the render of Singularity version 2 in its fork configuration that I made in Fusion 360. And here is the render of the anti-horizontal wedge configuration. Okay, we're now in Fusion 360, and it's now part of the video where we actually look at every single component of the bot in the CAD and break it all down. I think for this video we will start from the outside in. We'll look at the chassis, all the paneling first, the side plates, and then we'll take a look at the weapon, and then we'll take a look at the internals, and then after that we'll take a look at all of the interchangeable bits like the wedge setups, which we'll probably look at in the other file with the forks and this one. Alright, let's first take a look at the 4 side plates of the chassis, which similarly to Singularity version 1 is the main components that hold the chassis all together. So to begin, we have these inner side plates. They also double as the weapon mounts. So because we're running a live shaft design, the inner side plates now hold the indentations that the bearings will slide in, and then the weapon will slide into that. As you can see, we have a truss structure with a bunch of holes, similarly to the last version of Singularity. This is to save weight. Even though we're using plastic, this is a much thicker material now, so we are still cutting holes in it to save weight. And about the increase in thickness, unlike the first version, now the inner side plates are significantly thicker than the outer side plates. This is because we are using a live shaft design. So because we're using this live shaft weapon, there's no securing of the weapon from the outside because it's spinning. And because of that, we are now using completely the rigidity of the robot, especially that of the inner side plates, to keep the weapon in. And since stiffness is proportional to thickness cubed, having a thicker horizontal thickness is going to help with the weapon staying in. Alright, let's take a look at the outer side plates now. So the outer side plates are also going to be made of ultra high molecular weight polyethylene. And similar to the last one, the outside is kept smooth to act as armor so it won't be bitten as much. And the inside has pockets to save weight. Unlike the last one, the rear side does not have the hole anymore because of the way the drive is mounted. However, the front side still maintains that hole where the screws would go through and attach the front wheel. And you can see in the front there are 2 more holes. These are to mount the outer side plate to the wedge elements, which then mounts it to the inner side plate and the bottom plate. For all the side plates, there are holes on the bottom, and they allow the bottom plate to be attached to the side plates. You can see this also happens on the outer ones, the inner ones, and there's one in the back, and then there's two in the middle and the front. Attaching to all the side plates are the top and bottom panels, of course. Let's start with the bottom panel. So this right here is bottom panel. It is a big piece of 1/8 inch ultra high molecular polyethylene, and you can see it's going to be a flat 2D geometry, so this can be done on the water jet, which saves some costs. And it's mostly just to hold the side plates together. You can see there are holes on the outer side plates and the inner side plates. So we have screws that go in from the bottom through the bottom panel and then into the inner and outer side plates to hold it all together. And you can see there are some puzzled slots, and this is for the puzzle fits of the side plates to mount in. In the middle, this is where the center of the robot is, where all the internals would sit. And to save weight also, we have some truss structures so we can remove most of the material. Unlike the first one, this one is asymmetrical. This is because the motor is really big and it needs to have an extra opening to accommodate. Moving from the bottom plate to the top plates, there are two, because one goes onto the slanted structure of the inner side plate and one sits flat and holds the electronics in. So these two pieces are actually going to be made of carbon fiber. You can see here it is a flat piece of 1 millimeter thick carbon composite. Usually it's carbon fiber woven sheets reinforced with a resin. And on top, you can see this is the rear top panel and then the front top panel. There are also holes. With the rear top panel, there are 3 holes to attach to the inner side plate, 3 holes to attach to the outer side plate, and then there's 2 holes to attach to the rear armor panel. This is mostly to act as top armor, obviously, but also to increase chassis rigidity, especially in the horizontal direction. Again, because we're using a live shaft weapon, we need as much rigidity in the horizontal direction as possible. Moving to the top front panel, you can see here 2 more screw holes to attach to the inner side plates to add even more rigidity. Because this piece is closer to the weapon, it should do even more of the work. And then in here, we have 2 more screw holes. These will attach to the motor mount, which we will go over later in the internals to help with adding some structural support for the motor mount. But also there is a hole in the middle where the switch would go for the robot. One interesting bit here is you can see over here, let's just activate the entire robot. There's a hole here. This is where the motor goes for the weapon. Similar to the bottom, the weapon motor is so big that it needs a hole on top as well, which I think also looks pretty cool and should help with motor cooling. Moving from the top panels, let's go to the rear of the robot and look at the rear armor panel here. So similar to the old design of Singularity, this piece will be 3D printed. I think for this case we'll also make it out of Mark Forged carbon reinforced nylon, which should be really strong. This mainly acts as the rear armor for the robot. It protects the 2 drive motors in this case and the electronics inside. It is curved to fit the rear wheel geometry so that the rear wheels maintain contact with the ground the entire time. And that should be it for the chassis. Let's take a look at the weapon now. So this egg beater, as you can see, is a very traditional egg beater design. It's a rectangle with most of the mass on the outside. This gives us a very good mass to moment of inertia ratio. It allows us to store a lot of energy for the amount of mass we're putting in here. The big difference obviously is the live shaft. So let's just activate the weapon. The original weapon was this one. It is very different from the one that's currently used. You might have seen this one in the render. This is the original weapon design. However, this was basically deemed as impossible to machine and probably very expensive by me early in the design, so it was only really kept because I think it looked pretty cool for the render. The new one is a much lower cost solution. So, unlike the old one, this new weapon is a lot more geometrically simple. It uses a set thickness instead of a non-uniform thickness. This is so we can just purchase a steel stock. This is 1 inch thick, and then cut out the hole in the middle. The tooth, instead of being very complex, is simply just a circular slot that we can interpolate using a ball-ended end mill. And as you can see, because it's a live shaft design, the shaft is built into the weapon. It protrudes out of the weapon from both sides. This allows us, of course, to save a lot of weight by eliminating the shaft that runs through the entire system. That saved us about 100 grams, which then is put entirely into the weapon. As you may see, this weapon is a lot wider than the first weapon on Singularity version 1, and that allows us to better catch horizontals and also make the robot a little bit easier to aim in a vert engagement because the weapon is now wider. To attach it to the timing belt pulley, we're using a keying system. So this timing belt pulley is actually custom. It has a design that's optimized for 3D printing, and it uses a hexagonal bore here. This is because it was the easiest to machine the opposite onto the weapon. As you can see on the weapon, it has a hexagonal bit that keys into the weapon pulley and allows the weapon pulley to transfer all of its torque onto the weapon. The weapon pulley here is of a 22 teeth design, and it uses a 3mm pitch timing belt. To connect the weapon to the chassis, we're going to be using 2 sets of needle roller bearings. So over here you can see they are embedded in the chassis. These are going to be probably sourced from McMaster-Carr. They're needle roller bearings that the weapon shaft from the weapon will just roll on. They themselves sit static inside the chassis. I think that is it for the weapon system. We can go to the internals now. On Singularity, to service and build the internals, you have to take off the 2 top panels depending on what you're doing. So we're going to do that in the CAD as well, taking off the top front and top rear panels. And now we get a good look at the internals of Singularity version 2. Let's first start at all the mounting hardware that the internals will sit on. Over here is the motor mount. So this is probably going to be 3D printed as well out of carbon reinforced nylon. This is what holds the motor onto the chassis, as well as acting as some front armor behind the weapon. As you can see, in the front it has a semicircular design and sits very close to the weapon. This way it avoids being hit by the weapon. And on this side wall, this is where the motor mounts. So you can see over here, this is the weapon motor, and there are 4 holes in the back where the weapon motor could be screwed onto. The holes are not circular, but actually long in length. This way we can slightly adjust the motor. As you can see, we can slightly adjust the position of the motor and then slide it around to make sure the belt is perfectly tight. You have some screw holes on top. These will mount to the top panel, and then over here is a volume where the battery and the two Wago connectors would go. Mounting to the motor mount, of course, is our very oversized weapon motor. This is a Carnegie 42mm multi-star 610 kV brushless outrunner motor. It attaches to the weapon mount using 4 screws and attaches to the front to another custom 22 teeth timing pulley. As you can see here, with this timing pulley, there are a set of holes. This is because the front plate of this Carnegie brushless motor is designed to mount to a multi-rotor's propeller, and it has mounting holes. And these holes align with the mounting holes and allows us to mount this pulley to the motor using some machine screws. The other two 3D printed components are the battery constrainer over here. This orange component here is the battery constrainer. So the battery is this blue component in the chassis. This is the battery, and without constraint it would probably fly around and likely detach. That's actually what happened with one of the Singularity fights. We found out the battery was shaking internally and it made one of our switches detach. So having this battery be fully constrained is going to be a very important design goal, and I think this system should work pretty well for that. The battery constrainer is then constrained with the chassis by first this slot over here. So the chassis has the holes to save weight in the inner side plates, and it creates this triangular opening on top, and the battery constrainer slides into there on this side and is constrained vertically. And to constrain it horizontally, we have this one hole that attaches first to the motor mount and then to the chassis. The other thing that the battery constrainer does is it acts as a constrainer for the two lever nut Wago connectors that we're going to use to hold all of the wires together instead of soldering. This is because I wanted some more rapid replacement of electronics possibilities, and Wago connectors, they use a simple lever design to attach onto wires and should help with the process for assembly as well as potential replacements for the electronics. If you disable the Wago connectors, you can see they simply just slide in to the opening inside the battery constrainer. The last big plastic component in the internals is this electronics box. I will isolate it right now. It is also probably going to be 3D printed because it is a completely custom component, and it's what holds all of the other electronics, the receiver, and all the speed controllers into the bot. You can see here this area with the truss design. This is where all of the electronics would go. So in here I would probably Velcro in all of the receiver and all the speed controllers. And it also connects to the chassis using the same constraint technique that's used in the battery constrainer. You can see over here there is a slight protrusion that goes into the inner side plate, and over here there's this protrusion right here. This also goes into the inner side plate. This technique was actually developed for Singularity version 1 by Steven, and I think this is a really good idea, so we're also using it for Singularity version 2. Once the inner side plates are secured, this should be very much secured inside the robot without the use of any screws. It also contains this tunnel right here. You can see this tunnel is to deliver power to the left side drive motor. These drive motors have wires that go forward. As you can see over here, there are some stems for the wires. They would go forward into the electronics area of the chassis. But over here, since the battery is in the way, I created this tunnel. This tunnel with a hole here, so the wire would come in and go into this trussed electronics area where the speed controllers reside. And that's it for the current design of the internals for Singularity version 2. I think we'll now take a look at the drive section, and then we will look at the reconfigurable setup pieces. Alright, let's get into the drive section, starting with the motor and the gearbox. To access the drive section on Singularity, you have to take away the back panel, and then you can see the two drive motors and gearboxes. As for the drive gear motor itself, it is a Fingertech brushless Megaspark gear motor. They are commercial off the shelf, and you can buy them from Fingertech. And because they're commercial off the shelf, they are pre-made, so no assembly required, and they are very, very reliable. As you can see here, extending out of the motor is a very long D-shaft, and that's what the rear wheel attaches to. On the topic of the rear wheel, both the rear and front wheel will be 3D printed and completely custom. There is a separate file for the wheels here, and I will go onto them and explain the wheels in more detail. This right here is the design of the rear wheel of the robot. As you can see, it is made of two main components. A wheel rim, which is this component right here, and the tire, which will be cast. The wheel rim will be 3D printed, likely out of marked forged carbon reinforced nylon, similar to Singularity version 1, but this has quite some changes compared to version 1. Unlike version 1, which had a complex pattern inside, this wheel is just going to be a solid design that utilizes infill in the 3D printing process. Originally, we had the complex designed infill in Fusion 360 because we did not figure out how to do infill patterns properly for 3D printers. But now, since we know how to do infill patterns properly, we can now make a geometrically and weight balanced infill that will not make the wheel unbalanced when it is spinning. So we can now leave the wheel as entirely solid and let the 3D printer figure out the most efficient way to do it. On one side, the inside of the bot this time, there is the timing pulley. This is also designed for a 3mm pitch timing belt. This right here is not actually to make the motor power the wheel, as the D shaft is what the motor uses to drive the wheel. This is to actually use the rear wheel to drive the front wheel. As you can see later, the front wheel has the same timing belt pulley design, and we are going to run a timing belt from the rear wheel to the front to drive the front wheel. The rear wheel here is being driven by this D slot, which allows the D shaft from the gear motor to slide in, and because it is not round but a D shape, it allows the shaft to key into the wheel and thus transfer all the torque. On the outside of the wheel, there are these teeth. This is to make sure the wheel rim will transfer torque to the tire properly and the tire will not fall off during operation. The tire itself will be a urethane material that we are still currently developing. It will be cast around the wheel after the wheel has been 3D printed. The front wheel, as you can see, is very similar to the rear wheel. It is actually narrower than the rear wheel by 8mm. This is because there's less space in the front than the back, which is different from Singularity version 1. The big difference internally with the front wheel is that it does not have the 5mm D shaft. Instead, it has a round shaft similar to the wheels used on Singularity version 1. This allows a shoulder screw to slide in and act as the shaft. The front wheel also has the same 30 teeth timing pulley in the front integrated into the wheel, and this allows the rear wheel to be connected to the front wheel via a timing belt. And that should be it for both the rear and front wheels. Going back to the main CAD, let's take a look at the last component of the drive system, which is this little tray here. This is to hold neodymium magnets. Currently, we don't know how much excess weight we have with the screws on, so there's currently no magnets designed into here, but these trays are designed to slot into the bottom plate and mount neodymium magnets. The bottom of these trays are quite close to the ground, and that allows the magnets to sit really close to the ground and maximize their effectiveness. Now, let's take a look at the wedge components, which are the two setups. Since we're on this file, let's first take a look at this anti-horizontal wedge. There are three components in here: the big wedge element itself and the two mounting components. First, let's take a look at the outer wedge component itself. This wedge, instead of being made of steel like the last one, is made of titanium. Because of that, it is very lightweight, being only 81 grams, and it has 6 holes to mount to these two plastic wedge mounting elements. The corners are bent back to protect it further from horizontal strikes, especially from the side, to prevent that corner from being caught and the horizontal getting bite. To mount the wedge to the chassis, we have two wedge mount components. So these two right here. They are identical, left to right, so we'll only go over one of them. This acts as the main unifying component with the wedge as well as the front of the chassis itself. It of course also has the 6 holes in the front to mount the wedge onto, but it also has 2 holes in the side. This mounts it to the outer side plate. It has holes on the interior that mounts to the inner side plate, as well as 2 holes on the bottom that allows the bottom plate to also attach to it. This should in theory unify the entire front and help the entire robot stick together much better. A big design change that we also made from version 1 to version 2 is the shallowness of the wedge. Version 1 had a steep 45-degree angle wedge that we found quite difficult to get horizontals to ride up, so now we decreased the angle steepness to 60 degrees and is now much more shallow. This should allow us to get under horizontals much better and be able to kick them up much better. And now we move on to the fork setup that Singulariti will use to fight other vertical spinners as well as control bots. As you can see here, the front wedge is now gone and replaced with 4 forks. These forks themselves are made of abrasion resistant steel. They are 1/4 inch and are designed to be laser or water jet cut. Each individual fork has 5 holes cut into it, 4 for weight and 1 in the middle here to allow a machine screw to run through it, to allow the fork to be mounted to the bot and also articulate. The forks articulate so they always stay flush to the ground, and it allows our robot to get under other robots as easily as possible. The design makes them very, very shallow and thus allows minimal force for the opponent to ride up and be hit by the weapon in a very good angle. To mount the front forks to the chassis, we again have a front mounting element. This time it has slots in the front that allows the mounting of 2 forks per side, and a hole in the front that allows the machine screw to slide through and secure the forks to this mounting element. This will probably be 3D printed instead of machined UHMW because it is of a higher complexity, as well as being less critical, as well as needing less critical, as well as the strength being less critical compared to the one for the horizontal wedge. It also has 2 screws on the side to mount to the outer side plates, 2 on the bottom, and 1 on the inside that mounts to the inner side plate. Another addition for this setup is a 3D printed belt guard to guard the weapon belt and the weapon pulley. This is because we're going to be fighting a lot of vertical spinners, and vertical spinners that have a larger diameter to us might be able to aim for and hit our weapon pulley and break our weapon belt, disabling our egg beater. by having this guard here machined out of UHMW, it should be able to protect our belt and our pulley from direct hits from other vertical spinners. And that is it for the design breakdown of Singulariti version 2. We will keep you posted on the construction progress of this bot or any potential design changes. Thank you for watching. We'll see you next time.